This lesson is going to be on potential energy diagrams, which is often abbreviated as PE diagrams. Now, what they do is they actually show the energy of the chemical reaction over time. There's a couple vocabulary words we need to talk about before we get started, and then I'll show you how to do the graphs. The forward reaction goes this way, the way we read, left to right. Reverse reaction does the opposite. So we're going to have to worry about forward and reverse reactions in this. So when we talk about forward and reverse, this is the direction that we're referring to. Activation energy is the minimum amount of energy needed to start a chemical reaction. Think of it like a barrier. It's going to be shown as a hill. If you don't have enough energy to meet the activation energy requirement, then no reaction happens. Here's the example I usually give. If you take a match and you strike it on the little striker pad that's outside the matchbook, if you don't do it hard enough or fast enough, you don't generate enough heat through friction to light the match. That heat and friction, that heat from friction is the activation energy. So in other words, if you don't strike it hard enough, then it's the head of the match or the tip is not going to get hot enough and then the match won't light. That's exactly what activation energy is. It's the minimum amount needed to make that match light. Catalysts. They lower the activation energy. They also speed up chemical reactions, and they're used in digestion. The main thing that we're going to talk about here is that they lower activation energy. And I'll explain that in a second. And then inhibitors. Inhibitors are anything that stops that stops a catalyst. In food science, an inhibitor is basically a preservative. So the bacteria that digest our food, that make our food go bad, they use catalysts in order to digest the food. Well, something that stops their catalysts will make the food last longer. We call it a preservative. That's really all a preservative is. Now, catalysts, they lower activation energy. So if we look at this, this is a PE diagram. So I'm going to explain everything. We have our reactants here, and we have our products here. Now, keep in mind, since this level here, there's going to be some number over here, represents the energy of our starting material. And then this number represents, or whatever this number is at, it would be all the way over here, would represent the energy of our ending material. So think of it like money. If you started with this much money, and then you ended with this much money, well, you lost money because the total amount of money you had went down. Don't worry about the hill in the middle. If you started here and ended here, the middle doesn't really matter. So that would be what we call exothermic, because we're losing money. If the hill, for some reason, looked like this, where you started here low and ended high, this would be endothermic. So an exothermic and an endothermic PE diagram are basically the same thing. You start on the left, you end on the right. It's just starting high and ending low versus starting low and ending high, absorbing energy or releasing energy. So now let's go to the actual hill itself. So the activation energy would be the energy needed to get from your starting point, which is right here, to the top of this hill. We call the top of the hill the activated complex. If you notice, there's two. So here's what happens. Under normal conditions, you would need enough energy to get all the way up here. Okay, once you're here, you go over the edge. Think of it like if you were going to roll a ball over this hill. If you don't give it enough energy to get over to this top peak here, then it's just going to roll back down. Whereas if you give it just enough to get here, it will then roll down the other side on its own. That is the activation energy. Now, what a catalyst does is it takes the size of this hill and it shrinks it. So this big hill, if you had a catalyst, would become this small hill. So if you notice, I have them labeled differently. The bigger hill I call the uncatalyzed reaction, RXN, pathway. The smaller hill I call the catalyzed reaction, RXN, pathway. I'm abbreviating everything here. So if you notice, I have two forward activation energies because there's the energy needed to get over the big hill, and then there's the energy needed to get over the small hill. So this big amount right here, from here to here, is the energy needed to get over the big hill, and this small amount right here is the energy needed to get over the small hill. Remember, we're starting from right here. And so this dotted line right here is an extension of the reactance level. So we have the forward activation energy with a catalyst, or I would just say catalyzed, and then you have the forward activation energy without a catalyst. I would say uncatalyzed. So there's two. Now, we also mentioned that there's forward and then there's reverse reactions. So it turns out there's forward and reverse activation energies. So you could think of it this way. If you're rolling a ball over this hill, if you're right here and you're trying to roll a ball over the hill, right? You've got this option and then you've got this option. They require different amounts of energy. But if you were here where the products are and you wanted to roll the ball over the hill in the reverse direction, well, then you'd have two separate size hills. There'd be the energy needed to get over this small hill, which is represented here, the reverse activation energy catalyzed. And then you'd have the energy needed to roll it over the big hill, which is represented here, the reverse activation energy uncatalyzed. All right, so that is what catalysts do. That is what activation energies are. And that's why on PE diagrams, you'll always see two potential hills, because you have the uncatalyzed, which is always going to be the bigger one. And then you'll have the catalyzed, which will always be the smaller one. Now with this, abbreviations that I'm doing, I have a key here. This is how I'm going to be abbreviating it. Reaction, FWD, REV, AE, PE, cat, non-cat, and here's what they all mean. So now let's look at a full PE diagram.